So section 5 for us is sum and difference identities. So first I want to start you off with just kind of why in the world these identities exist in the first place. Well, we've looked at a lot of values on the unit circle that we can find. In degrees, you've got 0, 30, 45, 60, 90, and of course any iteration of those around the unit circle. These identities add to angles you can find by hand and give you a lot more variety of angles you could get. So for instance, sine of 15. If we can do combinations of adding and subtracting things on the unit circle to produce some other angle, then that gives us something that we could use these formulas to get. So an example of what I mean is, instead of saying sine of 15, that would be the same thing as sine of 45 minus 30. 45 minus 30 is 15, but if I use the formula for this identity, then I actually have something off the unit circle, ratios off the unit circle I can plug in and figure this out by hand without using a calculator. And also get an exact answer for it. So here are the properties. If for some reason you missed the proof and you haven't done that, you definitely want to check that out so you see why this comes to be. These are definitely things you do need to memorize, but usually just kind of going through it a few times, you'll kind of locked in. On the proof I did use A and B, but it all works out the same way. UV, AB, doesn't really matter what angle we call these, just make sure you put them in the right spot. So sine U plus V is sine U cosine V plus sine V cosine U. The big thing is plus or minus, whatever symbol you have here is what you're going to have here. I'll let you read through and commit to memory the cosine version. But whatever sign you have here, you'll have the opposite. And that's where this minus over plus comes from. It's kind of a weird symbol you probably haven't seen before. It's all it means. Whatever sign you have here, put the opposite sign over there. So just pure memory tricks that kind of come up over the years. So I just record them as people have ideas. They have no basis with proof. These are just kind of things people throw out. If they help you, good. If they don't worry about it. But sine is opposite. So when you look at the sine identity here, it's sine and cosine together, the opposite things together. Cosine's adjacent, so the same things next to each other. I don't know if that makes sense, but it's worked for some people. So with cosine, it's cosine, cosine, sine, sine, they're together. So if it helps you, good job. Not to worry about it. Sines, as far as remembering which one stays the same, which one changes. Somebody threw out this one time. Think about tangent. You got sine over cosine. Sine is on top, it stays the same. Cosine's on the bottom, it's backwards, it's flipped, however you want to reconcile that. So I just put on the numerator stays the same, denominator flips since cosine's a ratio. All right, rather than just give tangent away, you always have to earn your formulas in here, so I'd like to go through the proof with you. So let's run through and derive it. Most of this you should be able to do without any help whatsoever. There is one little trick step to it that basically was, as usual, someone sat down and stared at it long enough and said, what happens if I try this? And it worked. So that became kind of the most efficient way to prove it. But the first few steps I would expect you could do pretty easily on your own. Tangent is sine over cosine. So we can go to sine A plus B over cosine A plus B, which seems like a good step since we have identities for both of those at this point. And let's go ahead and expand those out. This will be a good time to practice your identities. So sine A plus B is sine A cosine B plus sine B cosine A. On the bottom, cosine A plus B would be cosine A times cosine B minus, because if that's a plus, this is the opposite, sine A sine B. This is the trick step here. There's a lot of ways you can probably reconcile this and eventually get there, but this is the most efficient route, and it involves kind of a weird idea. I'm going to take both the numerator and denominator and divide them by the same thing, which is okay, because if I divide them both by the same thing, it's essentially multiplying by 1. Doesn't change anything, it just kind of scales up the fractions. So let's take care of this step. What I'm going to do is I'm going to divide both of these fractions by cosine A cosine of B. Again, it doesn't change anything because I'm basically multiplying by 1. That over itself is 1, so it's okay to do that. Not something you typically would try to do, but I think you'll see pretty quick it's a nice thing to try. It's going to make this real efficient. So that's the idea. I'm taking numerator divided by that, denominator divided by that. And then we'll simplify it out and see what I get. So that's why I've got this really big division bar right here. So let's see what happens. If you take it term by term, both of these get divided by cosine A, cosine B. Well, cosine of b's go away, and you have sine a over sine a over cosine a, which is tangent a. So if you take this term and divide by this one, the cosine a's cancel out here, so sine b over cosine b, sine over cosine is tangent. So the same thing as tangent b, and that is a plus in between them. Now on the bottom, this part's really nice because that just becomes 1. You have the opposite sign, so minus here, opposite from what we started with. And then nothing's going to cancel out, but sine over cosine is tangent A. And sine B over cosine B is tangent B. And they're multiplied together. So that'll do it. Here's your more formal way to write that. So tangent of an angle plus or minus another one is tangent of one angle plus the other one. The sine is going to be the same. Whatever it is here, it's going to be the same there. On the bottom, you have 1 and then the opposite sign from whatever was here. And then tangent of one thing times tangent of the other. All right, so now we spent a lot of time proving them. Let's actually put it to the use here. So let's say that the angle we're trying to figure out can be defined by subtracting these two unit circle values. So we're trying to find cosine 2 pi over 3 minus pi over 4. So first up, I'm just going to go ahead and write that out with the identity. So cosine 2 pi over 3 times cosine of pi over 4. Whatever sine here it is here, we're going to do the opposite. And then sine of one angle, 2 pi over 3, times sine of the other angle, pi over 4. Now you want to replace these with the unit circle values. So another reason to make sure you're really quick with those unit circle values. All right, well, cosine 2 pi over 3, that's going to be 1/2, negative 1/2. Cosine pi over 4, that's here, that's going to be square root of 2 over 2. Plus sine 2 pi over 3, that's the y part, so that's going to be square root of 3 over 2. Times sine pi over 4, so that's going to be square root of 2 over 2. And now multiply what you can and combine what you can. So negative square root of 2 over 4 plus the square root of 6 over 4. And that's going to equal, I guess I could leave it that way. It's going to look a lot nicer if I say square root of 6 minus square root of 2. Just, it's nicer to put the minus between the signs and put them both over top of 4. And that's actually an answer you'll see pretty often. You'll start to see a lot of these kind of come back up, just like you did on the unit circle. So you'll sort of start seeing patterns among these as well. Now for this example, I'm giving you something, you've got to come up with two angles to get it, to figure it out. And you can get creative, you can do it however you want. It really, there's no right way to do it as long as the two angles add or subtract to make 165, your answer will come out the same. It doesn't really matter how you get there. Most people tend to go with 45 and 120 on this, so I'm going to start there. So the tangent of 45 plus 120. Again, no right answers. I mean, there's a right final answer, but there's no right way to get there. As long as you pick two angles that add or subtract to make 165, it's going to check out. All right, so let's practice the tangent formula. It's going to be tangent of 45 plus tangent of 120 over 1 opposite sign minus tangent 45 times tangent 120. So again, knowing unit circle values is helpful here. Tangent of 45 is going to be 1. Tangent of 120, that's over here, that's square root of 3. It's negative though because it's in the second quadrant. X is negative in the second quadrant. And then 1 minus tangent of 45 is still 1 times tangent of 120, which is still negative square root of 3. Kind of nice that you already found those already. So let's put together what we can. This is going to be 1 minus the square root of 3 on top. This is going to be negative square root of 3, but it is going to be turned positive, so 1 plus the square root of 3 on the denominator. The only problem there is that it's kind of like bad grammar. This could be written probably a lot more simple, but at least it could be written in a way that we can all kind of agree it's the same answer if we rationalize this denominator. So let's go ahead and rationalize that. It's 1 minus the square root of 3 over 1 minus the square root of 3. I said it backwards from the way I wrote it. But let's multiply things out. So 1 times 1 is 1. We're going to have minus 2 square roots of 3. And finally, we're going to have plus 3. Two negatives make a plus. Square root of 3 times itself is just 3. On the bottom, you're going to have 1. It's a difference of squares, so the middle terms are going to divide out. And it's going to be minus 3. Because square root of 3 times square root of 3 again is just 3. So put it together, see what we come up with. They're going to have 4 minus 2 square root of 3 over negative 2. Now, everything there can have a 2 divided out, so we need to take care of that. So 4 divided by negative 2 would be negative 2. And negative 2 divided by negative 2 would be positive. So the final answer, negative 2 plus the square root of 3.